All right, so once upon a time, back in about 1953, a group of Memphis high school kids got together and created the Memphis Astronomical Society. And here we are ever since. And did it go away? I guess not. That's all right. And that's what we are. And we're a educational society. We're not really a club. We try to be a club as much as we can, but we're an educational society and a 501c3, by the way, in case you feel like donating your vast inheritance. We'll give you a tax ticket to write off. Come on. There you go. And we have a QR code in case you want to sign up or become a member. That QR code takes you to a web page where you can enter your information and sign up to become a member. It's only $25 a year, good deal at twice the price. Or you can subscribe to our email list, and as someone has so astutely noted on there, you know, if you're going to get our emails, why not go ahead and join? It's only $25. So, but you can get our emails for free. With membership, you get our newsletter, access to our dark sky site, and a lot of other benefits, including an invitation to our annual company picnic, our annual picnic, which was a lot of fun this year. We have a calendar on our website. This month we have a telescope mentoring event. We do in Collierville at Hinton Park. It's not really, really dark skies. It's not really, really light polluted skies. It's somewhere in between. We get there before it gets dark and work with you to get your telescope set up, show you how to use it, hopefully learn a couple of things from you. And then, of course, after it gets dark, we can do some observing. And you can also even if you don't have a telescope, you want to see, if you're in a shopping for a telescope, you want to figure out what you want to buy. Come out, you'll see different examples of what our club members have and may get some idea about what you want. Then on Friday, July the 18th, we've got a Pinecrest event. We'll need some, I got to check with Mylan, but we need telescopes for this, right?
Oh, yes.
Yeah. So I'll be sending out a note to the Elite President Volunteers list. If you're on that email distribution, you'll get one. I expect an answer whether you can participate or not, and bring a telescope or not. You can just bring a laser pointer and point out stars or just help guide people around. So Friday, July the 18th, and that'll be 8 to 10 p.m. Saturday, August the 2nd is our next Hinton mentoring event, and that's all I've got on the calendar for this month. Am I missing anything? All right.
Hey, Rick, I can't see anything except you. Your slides are not on screen.
Well, let's solve that problem. Thank you, Bill. Is that more better?
Yeah, that's fine.
Once upon a time, back in 1953. So we'll go through here. I'll show the QR code for those that watch the video later and want to use that QR code. Use that QR code. Grab hold of it and sign up and get on our list. Here's our calendar, and of course you see what's on here. This is an interesting event. This is a significant event for me. This is what got me into astronomy. I found out that this was going to happen about a year, maybe two, before it did. Something in the news. I didn't know much about astronomy, but I was astute enough to realize that that was probably going to be a once-in-a-lifetime event, and I wanted a front row seat. And that started my search for a telescope. I had a Tasco 4.5-inch. I got it out in the most powerful 4mm eyepiece I had with it, and realized that that wasn't going to do at all. And went on a hunt for a telescope, and wound up, that's a whole nother long story, but I wound up with a great telescope that allowed me to look at the marks, the dark spot patches on Jupiter the night after the collision, because the night of the collision it was cloudy here. So, but it was so cool to see that, and I saw it all from my driveway in Memphis. Wasn't a member of the Memphis Astronomical Society, didn't know anything about it. The telescope weighed about 150 pounds, and I quickly realized that it was too heavy to go in the attic like my old Tasco was. And if I was going to keep it out of the attic, I needed to get involved with an astronomy club or something. I found the Memphis Astronomical Society, and I've been doing it ever since. So Shoemaker Levy 9 crashes into Jupiter next week. And then of note, let's see, we'll go ahead. New members this month, Damian Owens. Damian, are you on the Zoom call? I knew he wasn't going to show up. I work with Damian, and he called me about advice for buying a telescope, and I gave him some and told him about the MAS, and he joined right up, and probably never see him again. That's just the way it goes. Kevin Jones, thank you for joining. Michael Odell, Aline Maldonado, and Karen Boyer are all new members of the Memphis Astronomical Society. Anybody here in that list? You are. You're not on the list? Oh, okay. But you join?
Yeah, I'm not on the list, but
so I do. We kept trying to make sure we had the latest people on the list at the meeting. So this is as of the last board meeting. So, but welcome. And all right, we have a fabulous newsletter. And if you don't bother to read it, you really should at least open it up. I've got a couple of copies of it with me. You'll get our calendar, you'll get our monthly sky map with everything to look at, and sky charts, and some great articles. This month, you'll see an article from Steve about wanting input from you about the kinds of programs that we do. Steve is our Vice President of Programs, and you need to understand that without your input, you're going to get what you get. And if you don't like it, don't whine. But with your input, we will incorporate that and hopefully provide a better product for everyone. I will tell you that when we started growing and after the pandemic, some people thought we should move the meetings from Friday night till Monday nights. I've been doing this for 30-something years on Friday nights. I was outspokenly against it, almost belligerently so for some time. And then they took a survey, and the survey results could not be argued with, not even by me, and I'll argue with anything. And so we're meeting on Monday nights now. So if you think your input doesn't matter, or if you don't like the fact that we're meeting on Monday nights, make sure if that survey comes out again, you say so. But we want your input. We will try to accommodate. We still have an unused section of our newsletter. It's classified ads. This is if you have some equipment or something you want to sell locally, whatever. It's for members only, and it's non-commercial. Don't think you're going start buying stuff off of eBay and selling it to our members and classifying it and that kind of thing. It's just not into it. Thank you very much. We have a astrophotography group. This is a large section of what we do. A lot of our members are very interested in astrophotography. We have a very active group of learners and teachers in that space. And they meet once a month. This month there will not be a meeting, but they get together. They go out to our Astroflats dark sky location and set up and take data shots all night long till the wee hours of the morning and share their results with each other and their processing tips and tricks. And we got some PIX Insights experts, trust me. And so there's that. You've got to be a member of the MAS to be a part of the Memphis Astrophotography Group. We have swag on this Cafe Press site. We don't make any money off any of this. Don't run out and buy it thinking that you're supporting us. But if you want to support us by showing your proud membership in our fine organization, you can get your decorated doodahs there. Except for the key rings, I print those myself. They're up there in the bucket. Let's see. All right. Tonight we have Universes in Machines. Interesting title. And our presenter, Dr. Ben Keller, is here from the University of Memphis. I will let him get on to it. We're going to have to take a short break here while we switch around some equipment for the presentation. And thank you very much.
Great. All right. It looks like it's working on the main screen here. Can folks on Zoom see my slides? Got a thumbs up, I think I see. Awesome. Great. Yeah, so thank you for the warm introduction, Rick. It's always happy time for me to be back at the MAS. One of the first talks I gave here in Memphis since I joined the University of Memphis was here for the MAS. So I have a lot of fond memories in the 3 years I've been here. So those of you who have seen my previous talk, you can be rest assured that this isn't just a repeat of the same thing. This is a new talk I've put together, kind of a little bit of history, a little bit of philosophy, a little bit of math, a little bit of science, a little bit of astronomy, but a lot of what I'm interested in, because I myself am a computational astrophysicist, although recently I've been less interested in computing machines and more interested in organic machines. This is my son Isaac. He was born 74 days ago today. And you can see we've, of course, dressed him up in plenty of astronomy-themed onesies, although he's usually a little bit more happy if he has a bit more freedom to move around. So yeah, I have been thinking less and less about computational astrophysics, the sort of limits of modern cosmology and astrophysics, and I've been kind of getting back to basics in the last couple of months. These are, in fact, two of the books we read to Isaac before he goes to bed at night. They're quite fun if you have young children in your own lives. So yeah, if at any point I fall over or start drooling on myself tonight, you know the reason why. So yeah, today I really want to talk about astrophysics specifically in terms of computation, making calculations. And when you think about that, you're probably thinking of like cutting edge stuff. Things like the James Webb Space Telescope, the sort of most advanced observational tools we have today that rely on these powerful supercomputers to interpret and model and reduce the data that's coming from these things. So when we think of computation, we think of computers, probably think of the internet. Recently we're probably thinking a lot about AI and machine learning. We're thinking about modern stuff. This seems like a new phenomena, something that we've just started doing. But really, both in terms of astronomy and in terms of computational astronomy, these are ideas that have very, very deep roots in human civilization. These are concepts, tools, techniques, ideas that really stretch back to before even the dawn of agricultural civilization. So we found artifacts dating back thousands of years that anyone with two eyes can tell you this is in some way a representation of the night sky. We've got a crescent moon here, we've got stars, we've got a horizon, maybe another moon, the sun here. Clearly, the people who made this sky disk in Northern Europe about 4,000 years ago thought that there was enough important stuff going on in the night sky to represent it in this disk of copper and gold. Think about what do we keep images and artifacts of today. We might have pictures of our friends, pictures of our families, keepsakes from important moments or vacations in our lives. We don't just take pictures of dust bunnies. We don't take pictures of piles of trash. When we represent things, it is us representing things we think are important. Not only do we have representation in the sense of like images, we have writing. This is a cuneiform tablet from ancient Babylon. It's 2800 or so. Ooh, yeah, baby brain. 2100 years or so old, and recorded in this clay tablet is mention of an observation of a comet in the night sky that we have been able to piece together by going back to when this was written down, that this was an observation by a Babylonian astronomer done in September of 164 BC. So not only were these things important in the sense that we're going to visualize them, they're important in the sense that we're going to write them down too. And when we think about why did people find these things important, even thousands of years ago, before we had telescopes, before we had space travel, before we had computational tools, well, there's a couple of obvious reasons. And they all kind of come down to the fact that you can just see this stuff. If you look out at the night sky without light pollution, as every living human being would have done before the dawn of agricultural civilization, you see a really, really complicated picture up there. Not only do you have all of these point stars that seem to move through the sky, you also have these clouds of kind of fuzzy, diffuse light with fingers of darkness between them. This looks very, very different from the sort of day-to-day, on-the-ground stuff you see around yourself. Even more striking than what you see in the night sky is probably the sun itself. The fact that we have this cycle between day and night it's not just important, it's like the dominant thing that is going to set your daily calendar as a human being. Before we have artificial light, you're not going to be doing things after the sun sets because you are not going to be able to see. You're going to see the plants and the animals around you change their behavior over the night. So clearly, whatever this big glowing ball in the sky is, must be important. It's definitely important to you personally as an early human being. And if you're a very careful, observant early human being, you might also notice that not only does this thing rise and fall on a sort of daily cycle, over the course of the year, its position in the sky at noon changes. So this is a shape called the analemma. And you can make this image. An easy way to do this, if you're patient, set up a camera, fixed at a certain point in the sky, and take a photograph of the sun at noon, at its highest point in the sky, once a day, or in this case it's not quite once a day, more like once a week, over the course of the year, and the sun will trace out this pattern. So clearly there is this daily pattern of rising and falling, day-night, but then there's also this sort of annual pattern where the position of the sun changes, and this seems to correspond somewhat to the seasons of summer and winter, of fall and spring, when you're planting versus harvesting, when the animals are breeding versus hibernating. Again, if you are an early person, whether you are pre-agricultural or post-agricultural, this is going to be really important. Understanding this could potentially be the difference between you and your family living well for the next year, or you and your family starving to death. And of course, we have this other bright object in the sky, the moon. It's very different than the sun. It doesn't hurt our eyes when we stare directly at it. It has patches of light and dark, and even more strangely, sometimes it changes shape. It goes from being circular to kind of fingernail shaped over the course of what we now call a month. And on top of all of this, if you look at how the stars themselves move through the night sky, they seem to trace out this circular pattern. And if you're living in the right spot at the right time and you're observant enough, you might see that some of these stars seem to wander against the background of other stars. If you're a Greek person, you might call this a wanderer in your language, which would be, in Greek, planetes, or planet, wanderer. So there are these stars that are weird. There's this moon that's weird. There's the sun. Sometimes you might see these terrifying objects in the sky that never seem to be there other times, with these long tails. Perhaps they come at a time of flood or war or famine, and perhaps they are somehow evidence that that's going to happen. Even more terrifyingly, sometimes the sun itself disappears out of the daytime sky. And so, clearly, anyone, regardless of what time in human history they're looking up at the night sky, or the daytime sky for that matter, is going to observe that things are happening up there. Stuff is going on that doesn't just appear to be fixed, and it doesn't just appear to be random. There's some order to this. And so early humans who are looking up at the night and daytime sky realize that they can use what's happening up there. They can use it as a clock. So the most simple thing is you rise in the morning when the sun rises, and you go to bed when the sun sets. You eat when the sun is at the highest point of the day, noontime, and when it's in the morning and the evening. So you can use these things to set the clock of your day. You can keep time on longer scales as well, your calendar. You can use the position of the stars, of the sun and the moon, to know when to plant your crops, when to harvest your crops, when certain rituals need to be done, when birthdays happen, when historical events happen. So we can use these astronomical objects as timekeepers, both on the short scale and on the long scale. And early on, the order of this, to most people across the globe, seemed to suggest this is somehow a way to glimpse what's going on behind the scenes, the way that the spirits or the gods have ordered the world, and perhaps gain insight to the deeper, more fundamental makeup of the universe. This is an interesting thing to think about because, one, that's kind of still how we think about it today. We don't think about it as giving us deeper insight into the universe by revealing the plans of the gods. We think about it as giving us deeper insight to the nature of the universe by letting us see it on large physical length or long physical time scales. But we still think of the universe and what we can see through astronomy as revealing a more fundamental nature to reality. And when we think about people using astronomy as astrology, that is to predict their own personal life, the life of their family, the life of their city-state, maybe the life of their tribe or nation, we see that nowadays as somewhat primitive. But when you think about the fact that once you had a grip on how these cycles work, the cycles of the stars, the planets, the sun, and the moon, once you understood perhaps not the complete picture, but enough of that mathematical understanding that you could predict the future, why wouldn't you think you could also use that to predict the future in your day-to-day life? People thousands of years ago could predict decades in the future when the next eclipse could happen. In no other aspect of human life could you make a prediction like that with that level of precision. You could never predict when the next rainstorm is going to happen, when the next war is going to occur, how long, but you could predict down to the day when an eclipse would happen. So why wouldn't you think this is giving you the ability to predict the future? And so really people started to use these tools with our first kind of computing technology that human beings developed, which I would argue is written language. Written language gives us the ability to take ideas out of our heads into some physical, inorganic substrate. And one of the places where this has etched a deep, deep line in astronomy, even to this day, is in the early writing systems of Sumer and Babylon. So this is early Sumerian and late Sumerian cuneiform. These are numbers. This is their counting system. And you'll notice that it doesn't go 1, 2, 3, etc., etc. We jump from 1 to 10 to 60 to 600, 36. They're not using base 10. Sumerian counting was sexagesimal, or base 60. And if you have a watch on your arm, as I do not, you also have a sexagesimal counting device on you. The reason there are 60 seconds in a minute, 60 minutes in an hour, and 360 degrees in a complete circle is because the mathematical framework for doing that kind of counting was laid down first about 4,000 years ago in ancient Sumer. And in fact, the earliest writing about the night sky that exists comes from Sumer about 4,300 years ago. This is Enheduanna. She was the daughter of the king of Sumer at the time, Sargon of Akkad, and she was a priestess of a moon god. And so some of her poetry, this is the moon god, Nana, that she was the priestess of, some of her poetry actually describes the motion of the moon through the night sky. So this is, once again, talking about how early on the sort of two deeply, deeply intertwined ways in which human beings interacted with the night sky was through calendar usage, timekeeping, and ritual purpose, trying to understand their place in the universe. And so you could argue that she is the first astronomer. She is the first person to observe the night sky and write down what she sees. Calendar usage was also ubiquitous. So this is a 3,000-year-old. I don't believe these golden hats were actually worn as hats, but you find these kinds of artifacts throughout Northern Europe. They're called golden hats. I think it would be wonderful if they were worn as golden hats, because that would look ridiculous. But you can see this gold and copper cone, for lack of a better word, has a number of distinct rings, and on those rings are these individual humps or dots. This is a calendar system that is, we believe, used by these ancient people to convert between a lunar calendar, the number of times it takes between now and then for the moon to go from full back to full again, and a solar calendar, the amount of time it takes the sun to move to the same place in the daytime sky. If we go back even further and we look at megalithic structures in Europe, in Asia, Africa, North America, very, very many of them are aligned in a way that they have a major axis, such that the sun will penetrate a window at a certain time of year, or the moon will be visible down a shaft. In the case of Stonehenge here, maybe the most famous of these examples, the sun passes through a pair of these arches right over a sort of altar at the center during the solstice. So as the sun rises, it appears to be rising through this little gap here. So I've kind of already introduced a technology, writing, but it's probably not what you would think of when you think of as technology, especially when you think of as computing technology. But what I'm talking about here in this talk is really any kind of physical device that helps people think better. So in the case of writing, writing might not be a computational device in the sense that it lets us do math faster, like we think of modern computers here, but it is a computational device in the same way that this computer here can store far more books than I could ever memorize. Writing is a way of extending human memory. It's a way of producing a kind of memory that is far more reliable than human memory. If I write something down in a book saying that I caught a 60-pound cod off the coast of Newfoundland, and then I come back a year later, it's still going to say I caught a 60-pound cod. But if I'm telling you that story, it might be an 80-pound cod now. It also gives us the ability to share that information far further than I could individually. If I wanted to tell you that story, I would have to either gather everyone in this room and tell you all together like this, or I would have to go to each and every one of you one by one and tell the story. With writing, I can spread that to millions of people. And probably the most important thing about written language is it lets ideas persist beyond death. Prior to the existence of written language, we had oral traditions where a story might be memorized and passed down from person to person. But that vastly limited the complexity and accuracy of that transmission. So written language really extends our memory. But what we mostly think about when we talk about computing is our ability to calculate, our ability to do math quickly and accurately. So let's take an interlude here and talk about what do we mean in terms of math itself, because that math itself is a kind of technology. It's a social technology just in the same way that language is a social technology. The first humans who were able to speak to one another were not able to do mathematics because they had not developed mathematics yet. And in terms of the mathematics of astronomy, really early on, what's key is geometry. Because what's being seen by the early astronomers is the positions of things in the sky, the positions of things is geometry. And so the ability to take those positions and talk about them in a quantitative way was really the beginning of quantitative predictive astronomy. And the father of sort of quantitative astronomy is, at least in the West, this fellow here, Hipparchus, who's also known as the father of trigonometry, because these two things are deeply, deeply entwined. What Hipparchus realized was that the relationship between the sides of a triangle was intimately connected to the relationship between the point on the edge of a circle as it rotates around. And so what Hipparchus developed by giving us trigonometry was, for example, the ability to explain why eclipses happen. So if you think that the moon lies between the sun and the earth and that the eclipse is caused by the moon casting a shadow on the earth, well, trigonometry is going to tell you how big the moon has to be relative to the sun and how far away from the earth it has to be in order to cast a shadow that is complete and not a ring, or to cast a shadow that covers the entire sun before you might normally expect. And so Hipparchus's mathematical tools really were the dawn of doing astronomical calculation. And it led into, along with work from another Greek, Apollonius of Perga. I should mention, by the way, Hipparchus was from Rhodes, appropriate that we're here at Rhodes College today. Hipparchus and Apollonius were able to develop a tool called epicycles and deferents. And with those, you simply place an object, say a planet or a star or the sun or the moon, on a circle that rotates. And that circle's point, or that circle's center itself, so this thing that rotates is called the epicycle here, it rotates around another circle, the deferent here. And what that does is, from the perspective of this central point, maybe you or me, it allows you to have objects that appear to wander, planets, in other words. So this is the first point at which we can really start to lay down some math, some calculation, to do predictions about, say, for example, where the planets are going to be in the future, or when's the next eclipse going to occur. And so with that, we can actually start talking about taking these calculations out of the human brain and putting them into some kind of artifact. In other words, making metal do math for us. And the earliest examples of this were really just miniature models of the universe. So, for example, the armillary sphere, which was developed independently in a couple of different cultures. The one here we see is from the Ming Dynasty, fairly late, but we believe that the earliest ones in China arose about 2,000 years ago. You can see it's a number of nested arcs, nested circular arcs. And so the Earth would lie within the center of this armillary sphere, and the sun would be attached to one of these circles, the moon to another, the fixed stars on the outside, and an arc for each of the planets. And so this was a miniature representation of the actual model for the universe that people were working with at the time. So that use of trigonometry, epicycles, and deferents was put together into a comprehensive model for the solar system, which at the time was really a model for the universe itself, around 2000 AD by a Greek Egyptian by the name of Ptolemy. And this persisted for almost 1,500 years as the dominant model in the West for the universe. You have an Earth at the center that rotates, and then all of the other objects that we see rotate around that. You can notice here that the sun is kind of in between two sets of planets. That has to be the case to explain the observations they had at the time, that the moon can block out the sun. In other words, you can get eclipses. And both Mercury and Venus sometimes pass in front of the sun. So it must be closer to us. Meanwhile, Mars, Jupiter, and Saturn never appeared to do this. So they must be further away. And in order for these planets to be able to move in one direction and then turn around, wander in other words, they need to be placed on these epicycles. And so this model persisted for a long time, not because it was clean or nice or aesthetically pleasing, but because it worked. It made very accurate predictions about the positions of the planets. And it was so useful that it was embedded into mechanical tools. Probably the most widely used mechanical tool for about 1,500 years is a device called the astrolabe. If you have a planisphere today, which is typically two sheets of paper or plastic that rotate against one another, that's a simplified version of this astrolabe. It was originally developed by Ptolemy about 1,800 years ago, but it was really, really perfected about 500 to 600 years later during the Islamic Golden Age. And so what we're looking at here is the back of an astrolabe, and there's a couple of parts that are important to notice. So first off, you see there's a ring at the top. That's not just because it's a keychain. An astrolabe was used by hanging because this object has to lie, it has to hang such that it is perfectly vertical. And you could try holding it, but your hand's not going to be as accurate as hanging it from a string. And so this ring on top is attached to a piece called the throne. And you'll notice here there's a little movable device here that you can rotate. So you can rotate it like this or this. And there's two holes in it. And so this device is used for measuring angles. So you could, for example, if you wanted to measure the height of this tower, take your astrolabe, rotate this device so that you can look through both of these holes and see just the tip of the corner here. And you now know the angle from your astrolabe to the top here. And with a little bit of trigonometry, if you can just measure this distance, bam, you've measured the height. And of course, it can be used not just for measuring the angle to, say, the top of a building, but also to the sun, for example. And if you measure the angle to the sun, then all of a sudden now you can use this ring on the outside here to know what time it is. So the astrolabe was a clock. It was also a device for knowing where you were. So on the other side of the astrolabe, you would typically find a plate here. So the plate here is called the tympanum, and it lies within this outer ring called the mater, or mother, and it's etched with different lines. So those of you who actually go out and look through telescopes are intimately familiar with all of these different curves and lines on here. Zenith is the point directly overhead. Right down the middle here should be your horizon, or the Earth's axis. You have a horizon line here, Tropic of Cancer and Capricorn, as well as the celestial equator, which is the line that would get traced out if you took into account the Earth's axial tilt. And so the idea here is on the front of this tympanum, you also have this, in Arabic it translates to spider, device with the places you will find different stars. Each of these little hooks is some of the bright stars you might find in the night sky. And so what you can do is use your angle measuring device to find out where in the night sky a handful of these bright stars are, and then rotate your tympanum to place them in the correct location on your Alt-Az measuring device here, and thereby know what time of year it is, as well as what your latitude is. Now, you'll probably notice the fact that our zenith is here and our horizon is here depends on something. What's this going to depend on? Where you are on the Earth's surface. So this depends on your latitude. You can use it to measure longitude, but you're going to need a different tympanum for different latitudes. And so typically these astrolabes would actually have many different tympana embedded inside there. And if you were in Rome, you would use the Rome disk. If you were in Cairo, you would use the Cairo disk. If you were in Cordoba, you'd use the Cordoba disk. And this tool persisted for centuries. There was a Arabic scientist who wrote a book of 1,000 uses for the astrolabe. This was a tool for knowing the time of day, the calendar, predicting things like important feast days, knowing which direction Mecca was. This was a combination, calculator, calendar, GPS. This was kind of the smartphone of the early Middle Ages. And so the next step to go beyond something like this is to really start to have these pieces not just being moved around by you. In this case, with an astrolabe, every single piece has to be independently moved by the user. There's one central axis and everything rotates around that. To go beyond there, we need gears. We need different pieces able to interface with each other. And gears are an old technology. So we know that they've been used in kind of toys and curiosities for millennia. This is I love this one. It's a south-pointing chariot from China. The idea here is that you have a correct set of gearing here that cancels out any motion of these wheels. So if you lift this thing up, point your little man so that he's pointing south, and then place it down, no matter where you move this chariot here, presuming those wheels never sleep, that little wooden man will always continue to point south. You could also use these as drawing or architectural tools. This is a trammel of Archimedes. It's a tool for drawing an ellipse. But gears can do a lot more than that. Gears just inherently can multiply and divide. So if you take a look at these two here, the number of red gear rotations is going to be equal to the number of green gear rotations multiplied by the ratio of their number of teeth. So that's inherently multiplying this green number by something based on how you've set this up. And I figured I'd include this because this is a planetary gearing system. We don't necessarily just use this to model planets, but this inherently is designed around that epicycle and deferent model that was developed by Hipparchus and Apollonius and really refined by Ptolemy. And so the real peak of using gear technology, and arguably I would say the peak until about 150 years ago, is a device that we've only really quite recently even known about. So in 1902, a Greek Navy ship recovered a bunch of artifacts from a shipwreck just off the coast of the Antikythera island here. So this was a Roman ship. We think it was wrecked around sort of 2,000 years ago, and it had all the kind of things you would expect to find on a Roman shipwreck. Coins, jewels, rust, mud, ropes, but also a couple of big chunks of like rusted up metal. And so this was all, of course, recovered, sent to various museums. And one of the museums that it was sent to was actually curated by the brother of this Greek politician, Spiridon Stais. He was the Minister of Education at the time for Greece. And when he was visiting his brother, Lyridon, he realized that one of the items he had in display, that was this big chunk of metal, had what appeared to be a gear embedded within it. And this is that device. So this is the Antikythera mechanism's main component that we have. It's been somewhat cleaned up compared to what Spiridon would have saw about 120 years ago. But you can see that this is clearly some sort of geared bronze mechanism. Now, at the time that this was noticed, and as soon as it was sort of brought to the attention of the archaeological community, the fact that it was found on a 2,000-year-old Roman ship made the vast majority of archaeologists come to one single conclusion. This was something that was dropped recently off. This is out of place. Some fisherman threw some broken clock overboard or something along those lines. This is a modern piece of clockwork, because it does appear to be a clock that was just so happened to be dropped right on top of a shipwreck. And it wasn't until further developments, things like radio isotopic dating, that really showed, no, this thing is in fact 2,200 years old, that we realized that this is a truly, truly unique object. So the sort of pioneering work uncovering what this thing was done in a really, really seminal paper called Gears from the Greeks in 1973 by a Yale physicist named Derek J. de Sola Price. And what Price did, along with some of his Greek collaborators, was take the Antikythera mechanism, and we actually owe him a lot, because he could have taken this thing, scrubbed all the crap off of, taken it apart to try and figure out what is inside of it, and he would have destroyed it. This is how a lot of archaeology was done for a lot of time. But Price, being a physicist, knew that we have new non-destructive tools available to us to decipher this thing. And so he used a combination of X-ray and gamma ray imaging to actually take images at different depths throughout the device. And what that allowed him to do is things like measure out the radii and number of teeth for each of these different gears. And with that work, along with a little bit of inference, because a big chunk of these components are missing, we've been able to actually break down and reconstruct the Antikythera mechanism. This is one piece of the main ring, and you can see there are dozens of gears in here, rotating around about 10 different axes. And if you look at the radii of these gears, a major component of it corresponds to the epicycles and deferents for some of the major planets. And so this is sort of what we think the major layout of the Antikythera mechanism looked like. It was essentially two-sided, a little bit larger than a shoebox. On one face, you have essentially a calendar that shows the position of the sun and the moon, as well as all of the major planets. And it's driven by a series of gears in this upper level. What you do to work the machine is you have a hand crank that you set the position of the calendar to today, and you simply crank it forward until the day that you want to see in the future. Now, that day could be 1 year from now. It could also be the day in which Jupiter happens to be highest in the night sky between now and then. Meanwhile, on the other side, we have a number of different faces here, dials, that each correspond to different cycles. So for example, the Olympiad here would tell you when the next Olympic Games should occur. So we have encoded in here some bit of cultural knowledge. Meanwhile, if you look over here, for example, these two are the Saros and Exogelmos cycles. These tell you when the next eclipse will happen. So if you simply plug in when the last eclipse was, and crank this until the Saros cycle makes one complete rotation, the front calendar dial will tell you the date of the next eclipse. You can crank it even further using this longer term eclipse cycle, and it'll tell you the next eclipse 53 years or so from now. So this device, it really was a very, very early calculator. It was a calendar, a calculator, all encoded in this series of gears and all packaged in a bronze device not much bigger than a shoebox. And this was something that was built about 2,200 years ago. And essentially every technology that was included in the Antikythera mechanism was the height of our computational technology until about the early 19th century or so. So there's a quote from Arthur C. Clarke, the famous science fiction author, when asked about this in the mid-70s, because this was quite a remarkable thing. And Clarke said something along the lines of, if the insight of the Greeks had matched their mechanical ingenuity, we would be marching among the stars rather than simply puttering around the moon today. This really is an unbelievable artifact, and if it wasn't actually found, it would not be believed that ancient Greek technology would be capable of making this. And so this is really the first example of the major dominant early computing technology, geared calculators. So we didn't really start to see geared calculators pop up again until about 1,800 years later, during sort of what we consider the beginning of the Renaissance and the scientific revolution. So one of the earliest ones was actually invented by Blaise Pascal. So if you're familiar with Pascal's triangle, very famous French mathematician. Unfortunately, Pascal's calculator was not designed to do anything nearly as cool as calculate the next eclipse. He designed it because his father was a tax collector. And so this was a device designed to make calculating the taxes a little bit easier. And it's essentially two sets of numbers, one on the dials here and one on the dials here. And so you would plug in one number here, and then you would rotate a set of numbers in here, and this one up top would update itself to be the addition of those two numbers. Essentially, it was the same mechanism as if you think of a combination lock. So if you think of a combination lock here, right now it says 333. If I want to add 100 to that, I'll just click this up by 1. If I want to add 302, I'll click this up 1, 2, 3, 1, 2. And it'll show 605, of course. But when I click my numbers up, what would happen, for example, if I wanted to add 700 to this? Well, if I add 700, I'll go click, 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 click 7 times, and now all of a sudden it shows me 33. That's wrong. That's not true. What if I wanted to add 70 to it? Click, 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 click. Now I've got 303. That's also wrong. And so this mechanism alone isn't enough. What you need is something that can do a carry, that can take the overflow of one digit into the next. And that was really the invention that Pascal came up with that allowed this thing to work. This is the actual carry mechanism in the Pascaline calculator. It's much more complicated than the simpler model of a Geneva capture. So if you think of this green wheel, when you make one full rotation, which would be going from 0 all the way to 9 again, when it makes one full rotation, it causes one click, one movement on this. So you can carry the overflow from one digit into the next. But all Pascal's calculator could do was add, couldn't yet multiply. And so somewhat later, a device developed by Gottfried Wilhelm Leibniz, co-discoverer of calculus along with Isaac Newton, added multiplication and division in a device called the stepped reckoner. Beautiful piece of brass clockwork. And it essentially relies on the same mechanism here, but with these what are called Leibniz drums. So here you can see this is a thing that's designed to multiply by 3. So you get 1, 2, 3, and then the remaining clicks are skipped over. And this stepped reckoner that Leibniz spent about 20 years developing really was the basis for every mechanical calculator for the next 300 years. So what you can see here is the arithmometer. Amazing name. Why don't we call calculators arithmometers? This was the first mass-produced calculator. That stepped reckoner, Leibniz made 1. Pascal's calculator, he made 9. These were not devices that even a wealthy merchant would afford. These are basically curiosities for kings. But with the Industrial Revolution and the ability to mass produce devices at accurate scale, we now have the ability to buy things like the Comptometer, another incredible name, which was the first keyed calculator. So this is the beginning of being able to type in numbers, type in 1, 2, 3 plus 4, 5, 6, pull the crank, and have the result displayed for you. And ultimately, both of these devices inside were modified versions of Leibniz's stepped reckoner. And so once we had these kinds of devices, mechanical calculators that were adapted for mass consumption, we now had the dawn of the computer. Not in the sense of the machine, but in sense of the job. So the creation of these caused the creation of an entire new job class called the computer, which is a person that runs these machines in order to do calculations as part of some larger project. Now, I could give you a whole talk about human computers, but I want to focus today mostly on the machines. So just remember that these, along with a lot of very brilliant, very underappreciated people, made some very, very important discoveries. But I want to keep talking about the dead, the metal, the wood, the plastic, the glass, the machines. And to talk about that, I really need to talk about something that goes beyond Ptolemy's model. The mathematical tool that we really use nowadays, that is the basis of all modern astronomical calculations. And it's Newton's theory of universal gravitation that says that the force between two bodies depends on the mass of body 1 times the mass of body 2 divided by their distance squared. This is Newton's gift to us. It tells us why the planets move the way they do. And for the most part, it's essentially all the physics you need to understand everything from asteroids and planets up to galaxies and large-scale structure. There's a problem with this, which is this. Imagine you have one body, and you want to calculate the force of gravity between that one body and another body. So you have to do one calculation. So each of these lines is one calculation. So for two bodies, if I have the number of bodies versus the number of calculations, let's see how this grows. Because I don't know about you, But as far as I know, there's more than 2 things in the entire universe. So for 2 bodies, I have to do 1 gravity calculation. How about 3? Well, now I have to do 1, 2, 3 between each and every pair here. So for 3 bodies, I have to do 3 calculations. How about for 4? Well, now I have to do 6 calculations. How about for 5? Oh, man. Now I have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 calculations. How about for 6? Oh, now I have to do 15. 7. I have to do 21. It's blowing up on me. The amount of work I have to do goes as the number of bodies squared, which means if I want to do 10 times as many objects, let's say I want to go from calculating the 9 planets in the solar system to the 9 planets and the 81 largest asteroids in the solar system. So I have 10 times as many bodies. I have to do 100 times as much work. This means that Newton's gift is actually kind of Newton's curse for us. It makes this a really hard problem for human beings to do because it's a lot of work. But luckily, we have electronic tools that can work faster and more tirelessly than human beings. And the first use of an electronic computer for astrophysical simulation was done by a Swede named Erik Holmberg in 1941. And Holmberg had a brilliant light bulb idea, which was to use brilliant light bulbs to simulate gravity. Because just like gravity scales with 1 divided by the distance squared, the brightness of light scales as 1 divided by the distance squared. So Holmberg built about 100 of these little devices with a light bulb and a light detector. And so this light bulb represented how much mass was in a region, and this detector measured the force. And with that, he was able to actually look at how galaxies passing by each other can merge and scatter out pieces of themselves, all using light bulbs, all by putting the light bulbs down, measuring the output from each of his little photocells, and then moving them. And then doing it again, and then moving them. And doing it again. It was very time-consuming. So even though this was helping more than you would have if you were just doing this on pen and paper, it was still not scalable. It wasn't really until what we think of as modern Turing-complete computers, where all of the calculation is done in the machine itself, first with vacuum tubes here, that we were able to start doing real significant computer simulations. So this here is a computer called BESC that existed in I believe it was Denmark, could do about 10,000 calculations per second. And one of the uses of BESC was to figure out why some galaxies appeared to have bars. So what you're looking at here is a simulation from Lindblad, very famous astronomer, in 1961, using a computer called BESC. And each of these points here is a chunk of stars. And this is a galaxy disk, so it's about this line there is about 14,000 light years across. And watch here as this clock ticks away. It's ticking by in units of about 100 million years. You're going to see this ellipsoid here start to grow until eventually this galaxy that's nice and circular and symmetrical starts to develop a bar. And so one of the major things that we discovered once we had electronic computers was all of this class of beautiful linear instabilities, things that grow very slowly but require a lot of calculations to see. And so since we started to get to be able to do this, and we knew that a lot of calculations was the name of the game, the race was on to build the faster machines. So the next big leap came in the form of solid-state switching devices, transistors. And transistorized computers like the IBM 1401 let us go even further. So another question that was asked at the time, this being about 10 years later in the 1970s, was what on earth are these? This is the mice, what we know to be emerging set of galaxies. This is what we call a tidal tail. at the time, there were a couple of competing hypotheses. But two brothers, Alar and Juri Toomre, used one of those IBM 1401 computers to simulate a pair of galaxies merging together. Here you see another video. By the way, these videos that you're watching, they were made by printing out sheets, photographing them onto film. So these were very, very time-consuming, not just to produce the simulations, but to produce the visualizations as well. And as you can see, as these galaxies pass each other, these tidal tails are formed. And so this really revealed that, yeah, this idea that those things are from merging galaxies, it's the right answer. As we compressed our transistors smaller and smaller, eventually we merged them into single lithographed objects called integrated circuits, where you make an entire computing unit as one solid device. And this is what really brings us to today. This is what shoots us up to about 10 to the 18 instructions per second. And it's what brings us to kind of the modern supercomputer era. And so with these things, we can actually start to do really big simulations where we're now going beyond the point where you can see each individual particle. And part of the reason we're able to do that is not just the hardware, but the software. So in 1986, two astronomers, both of them still working today, if I remember correctly, Barnes and Hutt, developed a method called the tree code. And the idea here is, let's say I need to calculate the gravity force on this guy. Do I really need to know the details of all this stuff over here? Maybe not. Maybe I can just say all of this stuff has a center of mass here and a total mass that I can just say calculate just that. So in other words, rather than going to 1, 2, 3, etc., down to every single particle, distant stuff can just be averaged. You don't need to know the details of stuff that's far away. And so this calculation here in this example can take, say, 23 calculations down to 5. And so when you look at, for example, two merging galaxies and look at the tree around what would be the sun in each of these galaxies, you can see the stuff that's far away, you don't look at it in great detail. Only your nearby neighbors do you care about, because only those nearby neighbors are close enough to matter a lot for you. And this manages to take that n squared thing into n log n. So with an n squared calculation, if you wanted to do 1,000 times more work, it's going to cost you 1,000,000 times more time. With n log n, it's only going to cost you 3,000 times more.
So is this the equivalent of renormalization at the cosmological scale?
Somewhat similar. It's what's called an adaptive technique. And so this is what lets us do things like this. What you're looking at here is more than 1 billion particle simulation of the large-scale structure forming in the universe. And this has actually led to a number of discoveries as well. This is what you get for the large-scale structure of the universe if your dark matter particles are cold. This is what you get if they're warm, and this is what you get if they're hot. And you can tell just by looking at them, these are different. And so if we look at the clustering of galaxies, there's only one of these images that actually matches, and it's this one. So it wasn't until we could do these large-scale simulations that we knew that the dark matter that makes up most of the mass of the universe actually had to be cold. And so now we're moving beyond just calculating gravity. We're also including gas and stars. And typically we do this by either splitting our gas into particles or into cells, regions of space. And so with that, we can look at a lot of different pieces of physics. This is a really cool movie with too much going on. So before I start it, let me point out a couple of things. Bottom panel here, dark matter. Big panel here, gas density. This little guy, this is going to show you stars, what you would observe through a telescope. This is a zoom in of the inner regions of the gas. And these two numbers here are important. This is the mass of the galaxy in stars, and this is how fast it's forming stars, its star formation rate. Up at the top there is the time, and this is the length scale we're looking at. So let's watch as this galaxy forms over time. You can see its mass is growing, The rate at which it's forming stars is increasing, and the way it's doing that is by merging with other galaxies. This is what's called hierarchical structure formation, another thing that has been revealed to us through these simulations. You can also start to see we're forming a disk of stars and gas, but at this point, at redshift 3 or so, that's a little over 10 billion years ago, things are pretty messy. Don't really have a nice uniform disk. Over time, though, we're going to start to have this disk settle down. You're going to start to form a thin kind of plate or disc-shaped object. We're looking at it kind of edge on here. You can see it's thinner in this direction than in this direction. And all of this is just kind of happening. This is just emerging from the accretion of material into this galaxy. Here you can see now this color here represents the chemical elements that are heavier than hydrogen. These are metals, we call them in astronomy. They're made inside stars. But as we watch this over time, if you take a look at the inner zoomed in region of the disk, you can see it's fairly smooth. This is a zoom in from a very, very big simulation. And if we look at real galaxies, they're not very smooth. And that kind of leads us to the problem we're facing today as computational astrophysics, which is the problem of scales, length scales. So if you look at that large scale structure of the universe on sort of a 10 million light year scale, zoom in on an individual galaxy, which is kind of on the 10,000 light year scale, and then zoom in on an individual star forming region within that galaxy, which is kind of on the 10 light year scale. This region in which new stars are forming is 1 million times smaller in length than the region in which the galaxy itself is forming. And what makes that catastrophically expensive for us is that we live in a three-dimensional universe. 1 million times smaller in length means 10 to the 18 times small in volume. So in order to catch all of this naturally happening on the scale of galaxies themselves, we would need this many particles, which is, even for the computers we have today, out of reach. And so we have to deal with this by modeling things on the small scale using analytic approximations. So for example, if you take a look at a much higher resolution simulation like this one I've run, where you're actually modeling individual supernovae going off, over the course of millions of years, you can see it's forming that detailed, complicated structure of holes and bubbles and things within the gas disk. And so the next stage of this computational astrophysics question, what's next for the world, I think, is really to combine these classical computational techniques with machine learning and AI. So the idea here is you can take a simulation where a supernova will go off and blow one of these bubbles, and take this early period, which is very expensive to calculate, and have a machine learning model predict what the whole should look like. So you just skip to the end. And then the rest of the simulation continues as normal. So the question of, like, what are we talking about with computational astrophysics? It's not a question that really begins recently. And I'd argue it's not a question that's going to end anytime soon either. We're kind of just in the middle of it. We got 2,000 plus years of work on this question, and I think we've easily got another 2,000 years ahead of us as well. Even with simple tools, things like an astrolabe or even your eyes, you can do incredibly complicated and incredibly useful and insightful calculations. Even though we've known how to do a lot of these computing problems for a long time, the trouble is not knowing what math to do. The trouble is being able to build the machine that can do the math. And a lot of what we know today, whether it be that galaxies form by accreting smaller ones, whether it be that we live in a universe primarily made up of dark energy and cold dark matter, a lot of that has been learned not just through better telescopes, but better computers and better software. So I know I'm pushing, already on to an hour. So let me stop so we can get home at a reasonable hour and my wife can not kick my butt.
Questions?
Yep.
Okay, so the very beginning, what was the comet?
Oh, the one I showed there? I believe that was Hale-Bopp in that image. The one in the Babylonian cuneiform, that was Halley's Comet.
Okay.
That was Halley's Comet. Yeah. Yeah, Halley's Comet is, we know its orbital parameters well enough that you can go back more than 2,000 years and predict pretty much to the day when it would have been visible to the naked eye. Yep.
One thing I noticed early on in astronomy and religion is that no matter how primitive it may look to you, it's the same way as we are.
Yeah.
It fit what they need.
Absolutely.
It worked.
Absolutely. Well, that's the thing. I think that, like, if there's one thing that I want people to take away from this talk, is not that the tools we have today are better than the ones we had in the past. It's that the tools we have today are better because we had those ones in the past. We don't just leap into being as like having tools and technology. Every single step builds on the past. And so, like, you can't really criticize previous generations based on their knowledge or technology, because we ourselves wouldn't have our knowledge or technology if not for them.
That's why we lasted this long. We
Yeah.
had to adapt our technology.
Yeah, and that's why I really wanted to start with writing as the first technology, because writing is really, I think, the point at which we can start really truly building off previous generations.
Verbal didn't work.
No. I mean, great for telling stories, probably not fantastic for tables of astronomical observations.
There was no surprise. I forgot who it was in the 40s. It was did the first.
Holmberg,
Yeah.
Eric Holmberg.
And Switzerland,
Sweden, yeah. Lund University, yeah.
Yeah. So, that's the only place that he wasn't busy doing war calculations.
Yep. Sweden was neutral. Absolutely, yeah. That's could be a whole nother aspect, a whole nother hour of this talk. All of those electronic computers have their origins in military technology. There's also
today
still do. There's basically like two major uses for computing technology at the dawn of electronic computing, and it's weather prediction and military applications.
Weather prediction not being insignificant to military.
Weather prediction is so fundamentally useful. Yeah. Yes, yeah. Yeah, actually, there's a whole nother interesting story. Louis Fry Richardson is one of the originators of the fundamental concepts for parallel computing. He developed them to be done by human computers, but we use them now for modern supercomputers. He was a Quaker. And so during the 2 world wars, he was an English Quaker. He was drafted, was a conscientious objector, and so was put onto tasks originally in the First World War as a medic, working in a hospital, and in the Second World War, working for the meteorological office, doing weather prediction.
Feynman was famous for having introduced parallel calculations
Yep.
in the early.
Feynman did a lot of work on that. Von Neumann is another. There's the history of computing and physics are really tightly coupled. I mean, you go back, again, the stepped reckoner I showed in 1694. Leibniz came up with that. Also came up with calculus, which is like the fundamental basis. Him and Newton laid the foundations for both computing and physics.
When you mentioned calculus, you used the word discover.
Yes.
Was it discovered or was it?
That's a question. I could put you in touch with some of my friends in the philosophy department if you want an answer to that.
I love this. This was excellent.
Thank you.
Thank you very much. Anything else? We look forward
Okay.
to an extension
Well,
of this in
thank
some
you.
future. Thank you very much.
Thank you.
Thank y'all for coming out.